Welcome to the Maguire Iron podcast. My name is Brian Cooper. I'm the Director of Marketing at Maguire Iron and your host for this podcast. At Maguire Iron, we've been helping to store and protect quality water for over 100 years. On today's show, we will discuss water quality, water lab testing, and biofilm in water systems with Roger Miller of Water Systems Engineering. To help us learn more about water quality, lab testing, biofilm, and a host of other water chemistry topics, I am joined by Roger Miller of Water Systems Engineering, located in Ottawa, Kansas. Roger holds degrees in chemistry and biology from the University of Central Missouri. Roger has over 35 years of experience in multiple areas of the water industry and serves on many committees for national, state, and local water organizations. We are also joined by Jamie Mays, the Director of Sales for Maguire Iron and a NACE Level 3 Coatings Inspector. Gentlemen, welcome to the Maguire Iron podcast.
My pleasure.
Thank you.
Roger, let's start with what first interested you in water quality and the science behind it?
Well, I started my career in water actually on the industrial side of water and cooling towers and boilers. And water quality in that industry is really more based towards system fouling and corrosion degradation and system failures, leading all the way back to material selection. So that part of water quality in the industrial area was what I did for a while. I actually worked for Marley Cooling Tower Company for a number of years. I met John Sneeders in the mid-'80s, and he had started Water Systems Engineering with a laboratory that did assessments of water quality, not only in the industrial field, but also then in the potable industry. And all of the assessments that are made are basically analytical evaluations done by laboratory or in the field testing. So kind of like that, it was how I grew up in the industrial world and moved over into the potable industry. So
when you talk about water quality, what do we mean when we talk about water quality? Because that's a big term that gets thrown around a lot, but I don't think people have an understanding of what it specifically means.
It really is. I think it loses its value from time to time. But when you really look at water quality, it probably should be described as the evaluation or the assessment of a variety of characteristics in water that really are in relation to what are you using the water for. As I said, in industrial water, we're more interested in corrosion and the potential of fouling the system, where when you get over into potable drinking water, you're interested in safety and drinkability and usability from the standpoint of the consumer. So there's a lot of difference, but it is set into characteristics of water that you judge and evaluate. So.
Do you evaluate it from source to tap, or is there certain segments that you focus on predominantly?
We do both. Our laboratory is strongly groundwater. So what we're doing there is assessing the potential of the water as a raw source to foul the production well, which is the source of the water. Then we track that through to the treatment plant. And of course, we work with the treatment plant on what kind of problems are in that water now that you're going to have to clean up as a treatment specification and monitoring of their facility. So it's kind of a look at raw water. How is it affecting the system? Is it outside of some parameters that raw water might have? But of course, most of the parameters in drinking water are after the treatment spec, after the process, and then you have the primary and secondary standards for drinking water. So our lab kind of looks at both, probably more on the raw water side, the actual source water side.
So what kind of clientele does Water Systems Engineering deal with, or how do you guys get involved from that standpoint?
Yeah, from both surface water and groundwater. And like I say, we're much heavier into the groundwater industry. Our clientele stretch across the actual contractor that's working on the system, to consulting engineers, to actual municipalities, all of them that have an issue within their system, or they're a contractor that's been called in to assess a system problem. would maybe pull a sample and send it into our lab. And we're not a general testing laboratory. We're really what's considered a forensics laboratory or problem-solving laboratory. So even though all of the technologies we use in our laboratory are done by standard methods, which is a book of how you test water, we work within the standard methods, but we may go way beyond a normal general test for iron or manganese or total carbon if we think that that's some part of assessing the problem with the water supply.
Many years ago, I remember reading articles down in Texas where they were saying microbiological induced corrosion. Would a municipality who somebody's thrown that term around call you up and say, hey, I've got this issue, and then you would just go down, grab water samples and look for it? And how many different tests would you run if somebody called you suspecting they had that?
Yeah, I think that's one of the things, and I'll talk about it later in our discussion, but the whole aspect of the input of microbiology into the water industry has been phenomenal, mostly over the last 15 or 20 years, because we really didn't know a lot about biology. We just assessed, was it safe water, did it have coliforms or not? But the issue of microbial induced or influenced corrosion really goes back into the industrial world quite a long ways, because there are certain groups of bacteria, there's activities, oxidative bacteria that actually degrade steel and degrade metal, and so that corrosion aspect. But it's difficult to determine without testing if a corrosion damage has occurred because of water chemistry or because of water microbiology. So yes, that is an assessment that we would make in our laboratory, and we run both. We'll run a whole series of tests that are plugged into indices, the Langmuir Saturation Index, which tells us if the water is corrosive or not. But we also then do a bacterial study where we actually grow bacteria and we assess what type of bacteria are there. We run quantitative tests that tell us how much bacteria is there. And from that, we can assess that, yeah, this damage is probably, pointing towards microbially influenced corrosion. So yeah, we do a lot of that particular work. We're all members of the National Association of Corrosion Engineers and certified to different levels within the firm.
So we talked about water quality a little bit a few minutes ago. Are you guys seeing that be more and more important within the industry, and are you getting more people reaching out to you because of that fact to figure out these type of things in their water systems?
Absolutely. In each year or two, you'll see new parameters added to the primary and secondary drinking water standards. We'll probably see another 4 or 5 in the next 5 years added, various contaminants that we found in water. And yes, that seems to be more apparent and realistic in the world. Of course, we're all familiar with the Flint, Michigan issue and how that occurred and what really was the feedback on that. There's a lot of articles written in the AWWA journals and about that process. But yeah, water quality and how does this water quality problem come about? And that's really what we do is we look at the problem and say, okay, now how do we find what really happened? And that, in fact, we've got 2 projects right now that we're going out on that are exactly that. Hey, I've got this problem. What's causing it?
So you talked about groundwater a little earlier. What are the differences in those things that you're talking about, the groundwater versus other types of water? What does that look like? Right.
The industry, in most areas has either surface water supply or groundwater supply. What most people, the public, don't really know that most water districts also have both. They have groundwater wells even if they're right next to the river because of temperature gradients, and groundwater is a constant temperature. But groundwater is also cleaner because it's filtered through the subsurface. So we have less problems with purity and cleanliness and contaminants in groundwater than surface water. Of course, surface water is much easier to get. You just draw it right off of the river and into your system and start treating it. The groundwater wells, the dynamics of municipal wells, which are thousands of feet deep to a couple hundred feet deep, create all kinds of problems with fouling, and of course that's water that has come through the aquifer and the subsurface and has that water rock relationship. So sometimes we can get natural contaminants like nitrates that have limitations, but we're going to get them because of the water-rock relationship of groundwater being produced from the subsurface. So kind of the source is different, the treatment schemes are different, and certainly the problems are different.
So with the two different types of water, are there different things that lead to poor water quality? You touched on it a little bit with nitrates in, the groundwater, but surface water. What are the different things that can happen in those circumstances?
Well, of course, in surface water, we never know what's being, I guess you'd say, leaked into the supply source. So you do have a lot more contaminant problems with surface water. In groundwater, you probably have more natural contaminants. You have, number one, biology and various minerals that we do have limitations on. So when we really talk about that problem, we have naturally occurring issues with water quality. Like I say, it can be iron, it can be manganese. We control certainly nitrates and a variety of minerals. But we have organic contaminants also. We have the biology, and we're going to talk about biofilm and all of that. Definitely part of the issues in groundwater. And I think that's why we see the treatment schemes being so different, because there's different levels of problems. Surface water, of course, has much more sediment than groundwater, so you're dealing with more solids, so you have a lot more treatment schemes of solids removal and clarification before filtration or RO.
So when people send you a sample and your lab figures out, okay, this is the actual problem, do you go ahead and then help them develop a plan within their treatment system to say, this is how you need to take care of this problem?
Yeah, we do. That's part of our analytical process is a specific report where we not only identify the problem and generally the source, but we've always had that request for, okay, what do we do about the problem now?
Right.
So, yeah. So in the 40 years that water systems engineering has been doing this, we have quite a database of how we've resolved various problems. A lot of times the resolution is to clean the system. If it's a water well, a pipeline system, a storage tank, a clear well, a treatment plant, whatever it is, normally there's a treatment process or a cleaning process that needs to occur. The specifics of that cleaning process should be addressed to the problem you're seeing. And that's kind of how our lab ties it. Okay, here's the problem, and here's the specific way you should clean that problem. There's a lot of technologies out there in the industry that are kind of shotgun approaches. They're going to work 60 to 70% of the time. They're products or technologies or mechanical applications. But we feel that if we know more about the problem through the analytical process and the data review, then we can really direct that resolution to the problem that's been identified. Yeah.
And it must be nice having 40 years of data. So if you're dealing with a municipality that's next to another one that had a similar problem or in the same area, I'm sure it helps speed the process and makes it easier to find the problem.
Absolutely. And a lot of times, just like you say, we may have a call and a sample sent in from one municipality, and within a month or two, we'll get a call and a sample in from a municipality that's in the area, if it's groundwater or surface water, yeah, that they've somehow encountered the same problem. Because, especially in surface water, they're going to see it. It's coming down the river. They're taking water out of the river. That kind of problem is going to be identified. Groundwater is a little more specific just because it doesn't always track to the well that's right there near it. So it's a little bit different. But certainly we run into that kind of problems.
So we talked a little bit before, and you touched on it, on biofilm. What is biofilm for people out there who don't hold a biology and chemistry degree like you do?
Well, biofilm, it's really ironic because, 25 years ago, 20 years ago, we really didn't talk about biofilm. And I'm talking about in the water industry. Our judgment of bacteria in water was strictly, are the organisms that are present pathogenic? Do they cause disease? If they don't, we're fine. If they do, we have to do something about it.
Seems like a long time ago, doesn't it?
It does seem like a long, unless you're my age and been in the industry so long. But yeah, so probably I'm going to say 20 years ago, we did come up with the term, in the scientific arena, biofilm. We're members of the American Society of Microbiology, and a lot of their research is in the medical field, which we kind of cabbage onto in the water industry and utilized that information. And they started talking about biofilm. My dentist started talking about biofilm. Rather than plaque and tartar, he said, no, it's biofilm, And I said, well, gosh, I've been talking about biofilm for 15 years, But what biofilm really is not just the microorganisms that are present in the water, in the storage tank, in the treatment plant. It's their process of attaching and secreting a material called polysaccharide, which is, we refer to it as slime in the water industry, and the masses that grows, creating problems of water quality, lost production, fouling pumps, fouling valves. So that whole biofilm situation is in and of itself a major problem that we probably always had. We just didn't know really what we were dealing with.
Do we know where it really starts?
Yeah, bacteria are everywhere. The world runs on microbiology. If you think about it, your skin has microorganisms, your gut has microorganisms, so they're everywhere, and especially in subsurface if you look at groundwater.
Because you're talking soil, you're talking all kinds of rocks, all the stuff that have bacteria and stuff on it.
Absolutely. And so, when we think about that, we think, okay, well, there's really no pure absence of bacteria. Some people say in the clean rooms where we make computer chips, we might be as close to sterilization as we'll ever get. And of course, operating rooms, we thought we were back in the 60s and 70s, and we found out that's really a source of major bacterial infection. So, but they're everywhere, especially in water. But the proliferation, what an organism wants to do, and we call the free-swimming organisms platonic organisms, they want to attach to a surface. That's their life cycle activity. And once they attach to a surface, we call that a sessile organism now, he wants to divide and multiply and grow. And in that process, he secretes a lot of this polysaccharide material, and that mass starts to grow. And the Microbiology Society tells us that most waterborne organisms that we call slime formers, which most of them are slime formers to one degree or another, can secrete over 300 times their body mass in polysaccharide slime.
Wow.
So if you calculate in our laboratory, a fouled system can have millions of organisms per milliliter of water. So if you take millions or hundreds of thousands or millions of organisms, and now they all start secreting 300 times their own body mass, we have a massive slime that'll fill this room easily. So not only that, then that creates water quality and, like I say, lost capacity and all kinds of issues.
What are the early indicators of biofilm? You say this thing attaches itself to something, whether it's a steel water tank, a pipe, something in a treatment plant, and then begins to grow. How do you know you have it?
It's really difficult, and when we started working in the storage tank industry, it was even more difficult because a lot of the evaluations for biofilm were visual when you go in to inspect a water.
So you're saying seeing it floating on the top?
No, I'm saying
Okay.
you don't see it.
Okay, perfect.
That was a problem. Biofilm is generally not visible, very visible. Some bacteria will incorporate oxidized iron, the iron oxidizing bacteria, into their mass, and so you might see kind of a discoloration wherever as the first indicator. But in true evaluation, the only way you'll really know is to run a test, is to take a swab of a surface or to take a water sample.
And that's why I asked, because a lot of people will see something floating on the top of their water tank and go, oh, well, we have this. And that's not exactly what they're dealing with.
That's not exactly. Most of the time that's some type of airborne, material. But the evaluation of microbiology and the formation of biofilm can be easily quantified. And that's what you want to do is, okay, if we had 50,000 today and we test it again next year and we have 200,000, we know there's growth starting. And we'll talk about that in detail a little bit because as the bacteria and the biofilm mature, things change. But first indications generally are not visible. There's some form of testing that we see, or a lot of times the result of the biofilm formation is what we see. As biofilms start to grow and say in a water tank where you're chlorinating, you're disinfecting the water there, you have a difficulty maintaining a chlorine residual out there in distribution piping or storage that's because you're building a biofilm, and the chlorine's not going to just go after the bacteria. It's going to try to kill the microorganisms and the slime that it's formed. They're all organic material.
So you may be putting chlorine in your system at the amount that you think,
right,
but it's not doing what it's supposed to because the biofilm, it's attacking the biofilm and not staying in the water like it's supposed to.
Absolutely. And that's a lot of times, in storage or distribution where we really don't have a method to go get a sample, or you can't drain the tank and walk in and swab the wall every month. So then it's indicators. Hey, we're having difficulty maintaining disinfection residual in this tank. A lot of times when we do then analyze and evaluate that, we find that there's biofilm to a level that could be causing that problem.
I've heard people refer to it, say, at the bottom of a water bowl for their dogs if they haven't cleaned it out and they wipe their hands, and that's the same feeling. Absolutely. If you drain a water tower and doing your inspections, could you feel that same slime on the wall, or would it not get to that extreme?
No, in fact, like I say, since it's not visible, a lot of times in a surface area like a water storage tank, that's easily, you might not see it, but if you walk over and touch the wall and feel it in your fingers, it's kind of a slimy, and if you continue to rub it, it becomes more sticky. And
but
that's indication of.
But if I got the tank drained and I'm just going to put water on it and pressure wash it, it's all going to go away, right? Because I got chlorinated water. Yeah. Is that simple? And now I've solved my issue in the water tank.
Great theory. Great theory.
I think I know the answer to this.
Yeah, I think we're leading in that direction. But that's a great question, because one of the things that most people don't understand about chemistry and organics, such as biofilm, is that oxidative chemistry, which are disinfectants, chlorine and all the other various chemistries that we use, but chlorine, of course, is the predominant one, are what we call surface active chemistries. They have no ability to penetrate a mass. So in an oxidative reaction, it's like fire. It burns. So we're burning the surface of this big mass of bacteria and polysaccharide slime. We don't have the ability to go in and dissolve it and break it up. So if you just continue to chlorinate, and what little bit of research we've done in the area, power washing only removes a portion, only the very loose, I guess you'd say low-hanging fruit. And you don't really get a good clean-off of biofilm on a surface storage tank, is our experience, versus going in with an effective chemistry to clean that off.
Should people think about then just doing it as a routine as part of the inspection and washout program of the water towers? It's just, hey, we're going to just anticipate that we have it and change that process and use a chemistry and then a chlorine?
Yes, I think so. I think that there's credence to that without doing a lot of, I guess you'd say, evaluation process. We really are I guess, we're called in at the 11th hour when the system's, ready to be taken offline because the regulators are saying you can't use this storage tower or whatever it might be. So we see the worst case scenario. But yes, I think as we talk about in our industry as planned maintenance and preventive maintenance and better take care of our assets, that yes, you're not going to go in and power wash a storage tank or flush out a distribution line and effectively remove biofilm if it's starting to get, I guess you'd say, of any quantitative value at all. And it's been proven that the effective way is either mechanical scraping, which we can't do in storage tanks and even distribution lines, versus going in and dissolving it with the proper kind of dissolving and dispersion chemistry.
So at Maguire Iron, we deal with municipalities, rural water districts that have water storage tanks. Right. Are there different biofilms that grow in different storage tanks based on the type of tank they are, whether it's steel or concrete or glass lined, or there's a million different kinds out there?
Right. I wouldn't qualify it as different types of biofilms because the bacterial community in water is quite diverse. I mean, we have iron oxidizing bacteria. We certainly have coliform group of bacteria. But the effects are definitely related to the type of tank or the type of structure that the surface is. And we see and should see, activity of iron oxidizing bacteria in uncoated steel tanks or any kind of metal facility in the water industry, because that's their nature. There's only so much soluble iron in processed water, hopefully very little. So the food source for these guys has to be the oxidation of iron. So even in a coated tank where you have where the coating's been compromised and there's available iron, those bacteria will set up and use that as their food source. And that's a small group of bacteria, the true iron oxidizers, because they get their life cycle energy from the oxidation of iron. So they have to have available iron. So yes, we see that in metal storage. We see it in, like I say, compromised coated storage. The glass industry, we haven't done a lot of research here at Water Systems Engineering, but I just use a theoretical example that it's almost common thought to think that a bacteria that has to attach to a surface would have more difficulty attaching to a very slick surface like a glass-lined tank. I don't have any data or history to support that. There's a lot of theories about it, within the industry.
What about concrete?
Concrete's more of a unique situation, and going back now to my industrial days, even with Dr. Sneeders, the founder of Water Systems Engineering, we worked together years ago. We always knew that biofilm grew in the basins of cooling towers, which are all concrete, and it grew there much more than it grew up on the rest of the cooling tower. So we have always utilized the theoretical idea that porous surfaces, concrete being the one that you see most in the water industry, do provide a better environment, a better surface for biofilm and bacteria to attach.
Now, why is that?
Because it gives them an area that is secluded and protected. And if you look at a surface of concrete versus a surface of steel or glass or coating, there's a whole lot of protective areas for those first few organisms to set up and get started on the development of biofilm. So they kind of have this protection before they start secreting more of their own polysaccharide to protect themselves. But when we looked at, because we write a lot of reports on the various problems that are existing in the water industry in a variety of different areas, we always had referred to the fact that concrete helped bacteria and biofilm proliferate. We did a research project a while back, which was predicated by the fact we really couldn't find any concrete data that supported that, and we've been using that theory for over 40 years. There were a lot of quotes by very well-known microbiologists that said it has been observed, or we observed the fact that, yes, bacteria seem to grow more on the concrete surface than over here on the metal surface or another surface, but there was no concrete data. So we did initiate a little research project a while back, I can't remember if it was 4 or 5 years ago, where we did an evaluation and studied the effects of raw concrete versus coated concrete, metal, because we needed to provide an iron source for these bacteria to really proliferate. And that probably is the only information that I'm aware of that's statistical data that does show that there is a tremendous value in protecting concrete with coatings in the water industry rather than raw concrete from the standpoint of microbiology and biofilm. And that's a unique statement because people say, well, gosh, we've been building, concrete tanks and concrete storage facilities in the water industry for 100 years. Absolutely. But up until 20 years ago, we knew nothing about biofilm. So it is a new entity.
Well, Jamie talks about this a lot, is you're supposed to coat anything that potable water touches. But it's a regulation that nobody really wants to enforce. And I think it's from the standpoint of what you talk about. There's just so many of them out there. I don't think anybody can really get their arms around how you go about it and what you have to do there.
I agree. We actually, just to go a little further, we actually published an article in the Outflow magazine of American Waterworks Association about that research project. And I can't tell you the number of calls I had.
I'm sure your phone rang a lot.
From constituents, from competitors, from a variety of people. And basically that's what they said. My gosh, we've been using concrete and stipulating the fact that, number one, it doesn't corrode, so it's a great favorable material selection in the water industry. It has a lot of great value to it. And, now you're telling me that I need to coat it because of biofilm. Well, absolutely. And you probably, if you went back through all those hundreds of thousands of concrete structures over the years, they probably would show that they did have biofilm growing in them. And so that's kind of what that research project told the industry, was not from the standpoint of structure, not from the standpoint of corrosion or degradation of the structure itself, but just from the sheer fact that biofilm has issues. So if you allow it to proliferate, it's going to cause you problems in the future.
All right. So if you have this, and you've mentioned you have to use an acid or something to remove the polysaccharide slime to get down and to kill the bacteria, do those chemicals have an effect on the substrate? Maybe a coated steel or an uncoated steel or the concrete itself?
They would if you just use acid cleaning. Acid definitely can pit metal. Mm-hmm. Certain acids will go after components of concrete. They'll pit concrete. And that's what I say. We take the approach of kind of custom formulating the approach to cleaning. We know that in biofilms, we're dealing with organic materials. So what we would provide is recommendations for organic dispersants. And dispersant chemistry came into the industry, back in the 70s, where we actually had molecules that tried to hold everything apart. These are polymer-based chemistries. Most people in the water industry know polymers as bringing everything together and creating a flock or a sludge and clarifying water. Well, dispersion polymers do just the opposite. And in that process, and it's all ionic pushes and pulls with chemistry. So what we also saw was in big masses like biofilm, we are able to open them up and allow the acids and all of the whole formulation chemistry to penetrate the mass and then start dissolving it and freeing it up, which oxidation chemistry, disinfection products, don't do. So knowing what you got and knowing kind of the chemistry to go after it is really, I would say, the best approach. And like I say, there's products out there that are kind of that shotgun approach where it's got an acid, maybe a dispersant and a surfactant, which gives you some approach to that. But, we really like to point to specific acids because not all acids do the same thing, associated with dispersion chemistry, and then corrosion protection. Because like you say, on metal surfaces, unprotected metal surfaces, if you clean them with acid chemistry, you probably are going to start some corrosion activity. So we always incorporate an inhibitor. And in today's world, of course, you can buy acids with inhibitors already from the chemical vendor, but we always would stipulate that acid cleaning compound that we would recommend would have a corrosion inhibitor in it.
So groundwater comes in at a temperature of 55 to 57 degrees on average, right? And so we know that cold water usually will settle. It's a little heavier than hot water.
Right.
So when you start to see this issue, does biofilm grow at the top to where maybe stagnant water is versus down low where the fresh supply of cold water is coming in? And then if that is the case, would mixing of a water tower, keeping in homogeneous water zone, help reduce biofilm in a water tower?
I think it would. I don't really have any background to prove that, but I think, again, theoretically, yes, biofilm and bacterial activity is enhanced by temperature increase. There's other aspects of water chemistry that are increased by temperature increase. So I would think that, yes, you would have more potential for biofilm formation in those warmer zones and less in the colder zones. And so, yes, mixing should affect that. To a degree, I can't really
It can't eliminate it, but it might have some kind of effect just because now we're getting homogeneous chlorine mixture throughout the water tower.
And that's the quoted value to mixing, is you keep that homogeneous solution in the tank where you have complete dispersion of the disinfection product. So you get, hopefully, disinfection and bacterial kill throughout the tank zone. But also, the temperature gradient would certainly be a factor in what we're talking about as a biofilm formation.
So there's water tanks all over the country. Do you notice or have you seen by your data and your research in different parts of the country, as we talk about somebody in Florida where it's warmer year-round than somebody in Kansas, North Dakota, where it gets cold and then it gets warm? Does that make a difference in biofilm growth?
It does. Again, the bacterial population within water is so diverse that certain organisms are affected by temperature much more than others. So it's okay, do we have those particular organisms or not? I don't know that our database would really tell us the effects of temperature, but I think probably there would be some support that in the South, where you have warmer temperatures, longer periods of time, throughout the year, you probably would fight bacterial problems in those areas more than Minnesota or Dakota, say.
So we talk a little bit about chemical cleaning. We talked about mixing. Are there any other ways to combat biofilm other than, with chemicals or helping it with mixing?
Mm-hmm. I think biofilm is something that when we talk about the aspects of trying to control them, the benefit of knowing that you've got them early on, because if you're not established a massive biofilm in a storage facility or a pipeline system, then the disinfection protocol may control that. It's once they get started in this attachment and proliferation and growth and secreting all this slime material to protect themselves, that's when the real problems occur. So recommendations for, standard maintenance, standard evaluation, standard procedures of going in and not only assessing but also cleaning, periodic cleanings. To some degree, washouts would help that aspect, but chemical cleaning is probably going to be the better approach. But I think as we see in the industry, we're looking more to planned maintenance and preventive maintenance processes than we really ever have. I think, my 40 years in water are kind of unique in the fact that there have been periods of time where it's been almost a throwaway industry. We just run that well till it won't pump water, or we'll operate that pipe system till we can't get water to go down, and we'll just replace it. Well, as we've seen, costs have just grown exponentially. So we have problems now with the fact that especially in municipalities, can we get the funds to replace those assets like we did 50 years ago? And so that difficulty, and so what we've been preaching in the industry, and I think we're all on board, that planned maintenance and planned evaluation and go in and inspect the water storage facilities and everything that we can and maintain them better.
Is there anything we can do at Maguire Iron when we're doing a washout to assist our customers in helping recognize the biofilm other than maybe a potential slime? Is there a sheen, something that the guys may not be able to feel or see that then, my guys come off the tank, they can say, hey, Mr. Owner, I think you may want to send in a sample or something.
Yeah, like I said earlier, it's unfortunate because it's generally not visible. But yes, if they feel the wall of the tank and they feel that slimy, slicky feel, then that would indicate that there is starting to be biofilm, because that's not just bacteria, that's the polysaccharide material.
Should there be specific questions they may ask about chlorine residual drops, bad samples, or those would be the basic samples that they would ask or questions they would ask?
Yes, and that's the kind of questions we would ask of you if you sent a sample in to us to assess that. And it's generally in tanks is done by a swabbing of the wall, which bacteria doesn't grow uniformly. So generally you hope you hit it, but multiple swabs would generally give us a little better input. But we would ask, has the tank, seen issues in disinfection byproducts? Do you have a mixture in this tank? Do you have issues with not being able to hold chlorine or disinfection residuals? All kind of giving us a guideline. And then if we see the biofilm and the bacteria astronomical, it all ties together. Now, if we didn't see that, we'd have a discussion on what is the problem.
So we've talked a lot about biofilm. Are there any other things in the industry, in the water tank industry, that you guys are seeing here outside of biofilm?
Well, I think iron's always a big problem in throughout the industry, and it, the regulation now is to a point where half a part per million or milligram per liter is kind of the goal. That's sometimes attainable at the treatment plant. Generally, water can be cleaned up to that level, but as you can imagine, once it goes out into that system that hasn't been maintained and hasn't been cleaned and
You're talking about pipes and
I'm talking
all
about
that kind
pipes, yeah, and even some storage tanks, like I say, where you've got some buildup or you've got some void. So you do see high iron. Of course, corrosion is a bigger fact that it's going to create that iron throughout the system. But I think in storage tanks, what we mainly are looking for, because when I think about it, when we got into the storage tank area years back, you think about those issues versus raw water. That water effectively has been treated, filtered, balanced, chemically balanced, and disinfected. And for years in my history in the industry, we said, okay, that's great water.
That's perfect. Let's go.
It goes out there. Our customers are happy. There's no taste, odor, color. Everything's great. Well, now we know that was a fallacy, that we didn't really put it into clean pipes and we didn't put it into clean storage facilities. And so this great water that left the plant really wasn't as good as we hoped it was when it got to the tap. So,
talk a little about, is there any new technologies? You just mentioned it right there. 20 years ago, we thought this was fine.
Yeah.
How is technology evolving, or is the things you're looking for evolving, or are regulations getting to the point where it's pushing science to look for other things?
Well, absolutely. I think science in and of itself is pushing forward. But in reality, just like the whole biofilm issue of the last 20 years, quantitative assessment of bacteria. For years we used the heterotrophic plate count, which was you streaked an agar plate, you grew it in the oven, and you took it out
under a microscope.
Looked at it under the microscope, and you tried to count how many colonies were growing on this agar plate. Well, number one, a lot of bacteria, we found out later, a lot of bacteria are never going to grow on that agar plate.
And so you're completely missing them.
So you're missing a big portion of the available bacteria. Well, probably 15 years ago, we came up with a test called adenosine triphosphate, or ATP test, which ATP is a natural constituent to every living cell. So all bacteria have ATP. So a test was developed where we could extract the ATP out of all these little microorganisms present. We could measure that value, and then we had correlation data that would say, okay, and it was done by light emission testing. So it's a pretty standard theory. But then we could say, okay, we had so much adenosine triphosphate, which represents we had so many million bacterial cells in the sample. So it was a much more accurate quantitative value to what's there, and it was so repeatable, and it can be done in a very short period of time. You didn't have to wait 24 or 72 hours to grow the agar plate. So that was a big step in bacterial assessment in the water industry. Is it universally utilized? No. And do we have a lot of historical data? No. We've got hundreds of years of heterotrophic plate count data, but we probably only have 10 or 12 years of ATP analysis data.
Do you see that becoming more of a standard test as we move forward?
I do. In fact, I think there's going to be some other tests associated with the biofilm and the coliform issues. We just had the revised coliform standard 2 years ago. And in reality, I do a presentation for the water industry that we talk about the different characteristics that we look for in water. And it's really unique because we test for probably almost 90 different parameters now for the primary drinking water standards and the secondary drinking water standards. And in all those aspects, there's only 7 of them that are bacterially related, and none of them really try to assess biofilm. Like I say, those tests are associated with coliforms and Legionella and a variety of known bad guys in the industry. But no tests are looking at this whole mass of biofilm. And I think within the next 5 to 7 years, we'll see some, at least discussions within the regulatory community saying we really should be looking at the biofilm as a whole.
Well, that was my next question is, you talk about Legionella, and those are some of the, like you say, the bad guys in the industry that cause cancer and different things. Has there been any kind of study or long-term effects that we know of biofilm?
No, that's what I'm saying. Yeah, nobody has really correlated the aspects of this mass of material being developed within our water systems and how that affects. There's studies, like I said earlier, in the medical industry that we know what happens as biofilm becomes larger and the mass grows. And I always quote Dr. Shiraklis, who's a very prominent microbiologist and very active in the American Society of Microbiology. And his statement is that most of the organisms that we control in the water industry today as pathogens are what we call anaerobic bacteria. They don't need or want oxygen to live. And he also states that as biofilm grows and matures, most of the oxygen is initially used up by the aerobic organisms that like oxygen. So as a biofilm matures, it becomes more anaerobic, less oxygen available. Well, about 90% of the organisms that are in the coliform group are oxygen depleted organisms. So his statement is, as biofilm matures, you increase the potential of unsafe bacterial samples in this water source. Ideal presentation for storage, especially distribution lines. So if we can map biofilm and we can study biofilm, and we do in our laboratory, we make an assessment of a water sample as to what is the percentage of the microorganisms that we found anaerobic or aerobic. So if we just did our little simple test in the lab and we said, well, gosh, last year it was 30% anaerobic and this year it's 50% anaerobic or 60% anaerobic, that biofilm's maturing, and the potential of it causing you problems and being taken out of service by the regulatory issues is coming. So why don't you do something now and clean that biofilm out of there before you have a problem with it? And the first project we ever did in the storage tank industry, that was the case. It was a tower that the EPA had said, you cannot continue to use this tower. You have to clean it or do whatever you're going to do to it, but it's out of service. And we were called in and we ran over there and helped them with some kind of targeted chemistry for that problem.
So who's driving the regulations? The EPA, or is it a national level and not just the state agencies? Or
right.
The
national level produces the regs, the primary and secondary regulations actually, and they're kind of guided from the industry. We all have a little bit of input to it. But yeah, you're controlled from the standpoint of EPA, and it's all sampling based. They have to pull samples in pipeline systems and storage tanks, and certainly at the water treatment plant, and even from the raw water supply source, they are testing certain parameters, and all of that goes into the regulatory agencies. And like I say, if they find a storage tank or a distribution piping system that is out of specification, they have the authority to warn the utility or to shut the utility down. Now, the revised coliform rule in 2016, gave the owners a little bit more flexibility to resolve the problem first, advise what they're going to do, and it could be cleaning, it could be flushing, whatever, prior to the time of shutting down and advising the public for boil orders or whatever it might be. So there's been some changes in the way we treat the problem.
So you talked about Flint, Michigan a little earlier. After something like that happens in the water industry, have you seen a lot of changes? Do you see more changes coming down? Like, what does that look like in a regulatory stage that you end up having to help customers with?
I think the biggest thing, and what happened in Flint, as many people really don't understand, was they changed their source water. And we had a project, ironically, just the year before Flint, we had an industrial project that was the same situation, and they had tremendous corrosion damage. They corroded $6 million of piping in a matter of 2 years because they changed their water source from a non-corrosive water source to a corrosive water source, and nobody really evaluated that. It was easier to get. They were closer to the river, so why don't we take it out of the river?
Seems logical.
Seems logical. We had plenty of water. Nobody really looked at the corrosive aspects of the water. That happened in Flint. They changed the water source, became corrosive water, went out into distribution, a lot of old lead and copper sweated piping systems, and we started corroding it. We raised the lead level in the produced water. So it was a tragedy. Yes, we see more people looking at the raw water source, guidelines of what treatment technology they should be using over and above just the mechanics of it. What's the water chemistry? We just finished a project with an engineering company here in the area that was exactly what they wanted. Is okay, we think this is our problem. We conferred, we agree with you, that is your problem. And then they said, okay, what's the best way to handle this from the chemistry standpoint? They were a civil engineering company, so they knew the mechanical aspects of water treatment. They're saying, what should we be doing chemistry-wise? So yeah, we are seeing an increase in people looking more at the whole flow of what is this raw water, what do we need to do with it, what do we need to do with storing it and transferring it and all the other issues.
And at the end of the day, the more testing that is done from source to tap, the better it is for everyone, correct?
It is. It's a better input. It's better understanding of where you might have problems. Certainly, as we see large distribution and storage systems in a large community, you might be having problems in the east side of town, in the west side of town you're not, in the north side of town you got a different problem. So yeah, all of those things. I think you'll see more advised and standards, like from AWWA, their standards recommending you do those things. Will we see regulations that require and demand you do those things? That's a little harder, road to go down, I guess. But hopefully that will be, because I think that's the way to control the problems that we've seen in the industry.
Thank you to Roger Miller and Jamie Mays for helping us understand more about water quality, lab testing, biofilm, and many other water chemistry topics. Remember, you can always connect with us by going to our website, maguireiron.com. You can ask questions by sending us an email at info@maguireiron.com, or you can follow or reach out to us on any of our social media platforms. We're on Facebook, Twitter, Instagram, and LinkedIn. Thank you for joining us on the Maguire Iron Podcast.